Hello students, now we are going to discuss problems, your 45 problem session for Unit 7, Behavior of Perfect Gas and Kinetic Theory. It is your first problem, the value of critical temperature. Initially I told you the expression for critical temperature, critical volume, critical pressure, very important. So they asked in 1996 AIPMT exam. So we discussed about all three. It is 8A upon 27 RB. Next, the equation of state for 5 gram of oxygen at pressure P and temperature T when occupying a volume V. R is the gas constant. We know that what should be the gas equation. It is PV is equals to mu RT. P is given, V is given, T is given, R is given, but number of moles is not given. So we have to calculate this only. You know that molecular weight for oxygen is 32. It means if you have 32 gram of oxygen in your pocket, you can say I have 1 mole gas of oxygen. So 32 gram means 1 mole. So 1 gram means 1 upon 32 moles. So 5 gram means 5 upon 32 mole. So in this way we got the value of mu. In 5 gram how many moles are there? 5 by 32. So equation of state should be PV is equals to 5 by 32 RT. So we are going with option A. Next, two containers A and B partly filled with water and closed. The volume of A is twice that of B and it contains half the amount of water in B. If both are at the same temperature, the water vapor in the container will have pressure in the ratio of. They asked this problem in 1988 AIPMT. We know that vapor pressure will depend upon only pressure of vapor pressure is dependent only on temperature. So temperature is same, ratio should be 1:1. So we are going with B. Next problem is from 1989 AIPMT. A polyatomic gas with n degree of freedom has a mean energy per molecule given by. We know that what was the law of partition of kinetic energy. We know that kinetic energy is equally divided in its all degree of freedom. And we have one complete derivation before these 45 questions. And we saw there that with each degree of freedom, kinetic energy associated is half kT. If this molecule has n degree of freedom, total kinetic energy should be n times of half kT. Since kinetic energy or mean energy associated with each degree of freedom is equals to half kT. So energy with n degree of freedom, it should be n times the half kT. So kinetic energy of molecule should be n kT by 2. So we are going with option C. At constant volume, temperature is increased. We know Charles' law. We know if volume is constant, that Galois or Reynolds' law was there. P is proportional to temperature. If you are going to increase the temperature, pressure should increase. How you calculated pressure? With the number of collisions. Pressure is increasing means number of collision is increasing. So we will go with option B. Next, according to kinetic theory of gases, at absolute zero of temperature, what will happen? We calculate the kinetic energy of molecule. What was the kinetic energy of molecule? It was 3 by 2 kT. K and 3 by 2 both are constants. So if T is 0, it will become 0. It means molecular motion will stop because kinetic energy is directly proportional to temperature. Temperature 0 means kinetic energy 0. So they asked this problem in 1990 AIPMT. Next, relation between pressure and energy E. So we discussed in theory what was energy. We discussed in theory slides what we calculated there. That's why we did the derivation. P is equals to mc bar square by 3v. Every time learn means you should remember this relation for whole chapter. So what is this? It is 3pv is equals to mc bar square. If you want energy, multiply both sides by 1 by 2. So what now we are getting? What is energy? It is energy. So you can replace it by E. If you know this one relation, all problems are easy for you. Volume is not given, it means they are talking for unit volume. So what is the relation between pressure and energy now? P should be 2/3 of energy. So we will go with option A. Next, 3 containers of the same volume contain 3 different gases. The masses of the molecules are M1, M2, M3 and the number of molecules in their respective containers are N1, N2, N3. The gas pressure in the container are P1, P2 and P3. All the gases are now mixed. We know Dalton's law of partial pressure. So it means total pressure should be sum of individual pressures. So we are going with option C. This problem was from 1991 AIPMT. Again 1996, same type of problem. What will happen at 0 Kelvin? We know that kinetic energy is a function of temperature and we derive the relation kinetic energy was proportional to the temperature. Temperature 0, kinetic energy 0. So what will become 0? Kinetic energy. Next, at 10 degrees centigrade, the value of density of a fixed mass of an ideal gas divided by its pressure is x. What they are saying? They are saying कि mass divided by volume. We know that mass divided by volume is density. But what they are saying? X, they are saying x is density divided by pressure. Density divided by pressure is x. So in place of density, what you can write? You can write m upon v. So it is m upon v. What is PV? You know that PV is equals to mu RT. So what x become? X become m upon mu into R into T. So x become, so what we can observe at this place? We want a relation between x and temperature. What they are asking? Ki at 10 degrees centigrade, at 10 degrees centigrade, this ratio was x. What is the value of ratio at 110 degrees Celsius? So now you have relation. We only change the temperature, mass remaining same, number of moles remaining same, R is again one constant. So you can say कि whatever you are doing with temperature, what will happen? But x into t, it should be constant. It should be constant. But since we are writing capital T, it means temperature should be in Kelvin. So initially ratio was x. Temperature was 273 plus 10. What was initial temperature? 10 plus 273 means 373. What was final temperature? 110 plus 273. It is 280. It is 283. Sorry, 283. It was 283. What is this? 273 and 110, 383. So initial temperature was 283. Now if the value of ratio is x dash, temperature is 383, product should be constant. So you can say कि now this ratio will become 283 divided by 383 into old ratio. So we will go with option number B. They asked this problem in 2008. 11th, the number of translational degree of freedom for a diatomic gas is. Translational degree of freedom means there are only three axes: x-axis, y-axis, z-axis. So either it is monoatomic gas, or it is diatomic gas, or it is polyatomic gas. Number of degree of freedom associated with translational motion are always 3. 2 are associated with vibrational motion, and 1 was associated with 2 was with circular motion, means clockwise or anti-clockwise, and 1 degree of freedom with polyatomic gases attached with vibrational motion. So translational they are talking about, so it is 3 for all type of gases. If diatomic gas is there, 2 are related with circular motion, clockwise or anti-clockwise, spinning of electron. 12th, the degree of freedom of triatomic gas, 3 translatory, 2 clockwise anti-clockwise, and 1 is vibratory. So total 6 degree of freedoms are there. They asked this problem in 1993 AIPMT. Next, to find out degree of freedom, the expression should be, I told you, what is gamma? Gamma is 1 plus 2 by degree of freedom. But we want to calculate f in terms of gamma. So take 2 by f on this side and take this one on another side. So 2 by f means gamma minus 1. So f should be equal to 2 divided by gamma minus 1. So we will go with option A. It was the problem from 2000 AIPMT. Next, 1 mole of an ideal gas requires 207 joule of heat. To raise the temperature by 10 Kelvin when heated at constant pressure, It means you can calculate. This is a problem from 1990 AIPMT. So what is given, we will note. They are talking about 1 mole. We know that to increase the temperature of 1 mole by 1 unit, it is molar specific heat. If we are doing this work at constant pressure, it means it should be Cp. So what is the value of Cp? Cp means for 10 Kelvin you require 207 joule. So to raise the temperature by 1 Kelvin you require 207 divided by 10. It means it should be 20.7. Cp is given. If the same gas is heated at constant volume, to raise the temperature by 10 Kelvin means Cv. Cv means to raise the temperature, heat required to raise the temperature of 1 mole of gas by 1 Kelvin. But if you want to increase the temperature by 10 Kelvin, it means heat required should be Cv into 10. It means you want to calculate Cv into 10. Now how to do? I told you one formula. In joules, Cp minus Cv is equals to R. So what is the value of Cv? Cv is Cp minus R. R value is given in joule 8.3 and Cp was 20.7. So 20.7 minus 8.3, what we are getting? It is 12.4. So what energy you required? Cv 12.4 into 10, it should be nearly 124. What is it? 124. So we are going with option B. So problem was not very tough, only on the basis of definition of Cp and Cv. Next, for a certain gas, it is from 1990 AIPMT. For a certain gas, the ratio of specific heat is given by gamma is equals to 1.5. For this gas, Cp, Cv, they are asking about. First see gamma. They are saying gamma is 1.5 means 3 by 2. You know that gamma is equals to 1 plus 2 by n. Gamma they are saying 1.5 means 3 by 2. So gamma we can calculate by degree of freedom also. So in this way we cannot proceed. So what we will do? We will go by definitions only. We will go by definition only. We know that because that known gas is not there, na, they are saying gamma 1.5. So it means not monoatomic, not that type of. So they gave 1, means assumption is there कि if gamma is 1.5, what should be the value of Cp and Cv? So we have one relation for all gases, Mayer's formula, Cp minus Cv. In all options they are dividing by J, it means they are talking about calories. So Cp minus Cv is R upon J. What is gamma? For all gases, it is the ratio of Cp upon Cv. Maybe it is mixture of gases. So Cp upon Cv is equals to gamma. They are saying it should be 3 by 2. 1.5 means 3 by 2. So, two unknowns, two equation. We are able to calculate Cp and Cv both. So, we will calculate for Cp. If not getting answer, we will go for Cv. So, Cp should be 3 by 2 of Cv. So, in place of Cp, I am writing 3 by 2 of Cv minus Cv is equals to R by J. 3 by 2 minus 1 means 1 by 2. So, Cv by 2 is R by J. So, for this gas or mixture of gas, Cv should be 2R by J, not 5R by J, not 3R by J. So, these two options are wrong. Now, we will go for Cp. What is Cp? Cp is 3 by 2 of Cv. So, we are going with 3 by 2 of Cv means 2R by J. So, what we are getting the value of Cp? 3R by J. For this mixture of gases, Cp is equals to 3R by J. Yes, two options are there. In one 3R by J, in one 5R by J. So, we are going with option B. So, it was for problem based on Mayer's formula and definition of gamma. Next, again same type. It is asked in 1991 AIPMT. For hydrogen gas Cp minus Cv, they are saying A. For oxygen gas Cp minus Cv is equals to B. So, the relation between A and B is given by, we know that for all gases Cp minus Cv is either R, or if you want calculation in calories, it should be R upon J. It is not for oxygen, hydrogen or nitrogen. So, it means A should be equal to B, concept of that Mayer's formula. So, we are going with D. Next problem, which is from 1992 AIPMT. If for a gas R upon Cv is equals to 0.67, this gas is made up of molecules which are, so we know three type of gases, we will try to find from them, otherwise we will go for mixture of gases. So, they are saying Cv is equals to 0.6 by 7 means 2 by 3. Take on that side. So, Cv they are saying they are saying R upon Cv is equals to R upon Cv is equals to 0.67, means R upon Cv is equals to 0.67 means 2 by 3. So, Cv they are saying 3 by 2 R. We got the point. 3 by 2 R Cv is the value for monoatomic gas. We discussed in theory just before the crash course sheets. C. So, we are going with C. Next, 1 mole of an ideal gas. It is a problem from 2004 AIPMT. 1 mole of an ideal gas at an initial temperature of T Kelvin does 6 R joule of work adiabatically if the ratio of specific heats of this gas at constant pressure and at constant volume is 5 by 3, the final temperature of gas will be, we know that just in previous unit we have a derivation, work done in adiabatic process. What was is? It was R upon gamma minus 1 into initial temperature minus final temperature, it was given. So in this problem, each and everything is given. They are saying Ti, initial temperature was T Kelvin. Work done, it was 6 R joule. And the ratio of specific heat at constant pressure and constant volume, Cp upon Cv, means gamma is given 5/3. So easy to calculate Tf. They are saying it should be 6 R. Gamma minus 1 means 5/3 minus 1. Ti minus Tf, T minus Tf, 5/3 minus 1, cancel R with R. So this implies 6 is equals to, after taking LCM, take 3 in numerator, 5 minus 3, it should be 2. T minus Tf. 6 2s are 12, 12 3s are 4. So 4 is equals to T minus Tf. It means final temperature should be T minus 4. So we are going with D option. 19th, the molar specific heat at constant pressure of an ideal gas is 7/2 R. The ratio of specific heat at constant pressure to that at constant volume is, they asked this problem in 2006 AIPMT. Problem was very simple. Based on Mayer's formula, what is Cp minus Cv? It is R. What they are saying, molar specific heat at constant pressure, they are giving you Cp 7/2 R. Put the value of Cp 7 R/2 minus Cv, it is R. So what should be the value of Cv? It is 7 R/2 minus R. Take LCM, 7R minus 2R, 5R divided by 2. It is Cv. So now it is easy for you to calculate Cp upon Cv. They want to know about this ratio, which we denote by gamma. Cp was given 7R divided by 2. Divided by Cv means multiply and reverse the ratio. So it should be 2/5R. So what we are getting, cancel 2 with 2, cancel R with R, and you are getting now 7/5. So it is 7/5. So we are going with option B. It was from 2006 AIPMT. Next, the mean free path, 20th problem, they are talking about mean free path of a gas is inversely proportional to. See, mean free path is denoted by lambda and is given by 1 upon pi. D is diameter of gas, n is the number of molecules, √2. What is happening and what do you mean by mean free path? When molecules are moving here and there in a container, they are colliding with each other. The distance travelled by a molecule between two collision is known as free path. Means it is a molecule It is colliding with this molecule. After this, it collide with this molecule. So distance traveled between two collisions, it is known as mean free path, and mean of free path is mean free path. So derivation is not in our syllabus, so you have to remember the formula only. So what is the ratio relation with diameter? Same should be with radius, because diameter is 2 times the radius. So in terms of radius, we can write this formula 4 pi r square n raised root 2, means lambda is inversely proportional to square of radius. So we will go with B, because they use inversely, means 1 upon that is given in question only. The mean translational kinetic energy of a perfect gas molecule at the temperature T Kelvin is. We have a complete derivation in our slides before starting first problem. Ki for translatory kinetic energy for perfect gas means energy associated with all 3 degree of freedoms, means 3 upon 2 kT. We were writing K there, but they are writing KB. B for Boltzmann constant, because K was the ratio of 2 constants. So this new constant is known as Boltzmann constant. So sometimes they are writing it KB. Next, 22nd problem. The average translational kinetic energy of oxygen molecule at a particular temperature is 0.048 electron volt. The translational kinetic energy of nitrogen molecule whose molar mass is 28 in eV at the same temperature is, we know that energy associated with each degree of freedom half kT. K is constant for all gases. Only T can change the kinetic energy. If T is same, energy should be same for all molecules. If they are talking about only translational kinetic energy, it is 3 by 2 kT for mono, for dia, for polyatomic. All molecules have translatory kinetic energy 3 by 2 kT. Since they are saying temperature is same, so this translational kinetic energy should be same. So we are again going with 0.048. Next, 23rd. A cylinder contains 10 kg of gas at pressure of 10 to the power 7 Newton per meter square. The quantity of gas taken out of the cylinder, if final pressure is 2.5 into 10 to the power 6 Newton per meter square. Problem is not very tough. Why? We did complete derivation. I told you, remember only one formula. How you calculated the pressure? Pressure inside the container, it was P is equals to mc bar square divided by 3V. If container is same, means volume of gas is constant, temperature is same, C bar is not going to be changed. It means for this problem, P upon M, it should be constant. Getting my point? In this problem, P upon M should be constant. If initial pressure was P1, initial mass was M1. So P1 M upon M1. If final pressure is P2, mass is M2. So P1 upon M1 should be equal to P2 upon M2. We want to calculate what mass should be removed from the cylinder so that pressure will decrease up to this point. So first we will go for M2. Then we will calculate what mass you remove from there, means M1 minus M2. It is your final target. So M2 should be equal to P2 by P1, P2 by P1. M2 should be equal to P2 by P1 into M1. What is P2? 2.5 into 10 to the power 6. All physical quantities are given in SI units only, so no need to worry about unit. M1 was 10 kg. Initial pressure was 10 to the power 7. Cancel this 10 to the power 7 with this 10 to the power 7. What we are getting? M2 is equals to 2.5 kg. Means if you want the pressure inside the cylinder, 2.5 into 10 to the power 6 Newton per meter square, mass should be 2.5 kg, but it was 10 kg. So you have to remove the mass by the amount 10 minus M1 minus M2 we want to calculate. 2.5 means 7.5 kg. So remove 7.5 kg from the cylinder. So we are going with option A. Next, the average kinetic energy of a gas molecule at 27 degrees centigrade is this. Its average kinetic energy at 227 degrees centigrade will be, again a very direct problem. You know that kinetic energy, say U, is a function of temperature. So kinetic energy and temperature, this ratio should be constant. Means initial kinetic energy upon initial temperature. It should be final kinetic energy upon final temperature. So final kinetic energy, if you want to calculate, it should be initial kinetic energy into final temperature upon initial temperature. And now what is given? U1 is given. Initially kinetic energy was 6.21 into 10 to the power minus 21 joule. What was initial temperature? Capital T means Kelvin. So add 273. So 27 degree Celsius plus 273. We are getting 300 Kelvin. T2. It is increased by 200, so add in final result 200. What we are getting? 500 Kelvin. So now we can solve it. 6.21 into 10 to the power minus 21 into T2 means 500 divided by 300, this joule. Cancel this with this. 3 2s are 6, 3 7s are 21. So what we are getting now? 5 7s are 35, 5 2s are 10. So 10.35 into 10 to the power minus 21 joule. So we are going with C option. Next, two perfect gases having masses M1 and M2 at temperature T1 and T2 are mixed without any loss of energy. If the molecular weights of the gases are M1 and M2, then the final temperature of the mixture be We know that the formula for final temperature, it should be N1 T1 plus N2 T2, or if you are writing mole by mu1 T1 plus mu2 T2 divided by mu1 plus mu2. Only we have to calculate number of moles. So number of moles, mu1 means mass was m1 and molecular weight was m1, and mu2 means mass was m2 and molecular weight was m2, means m2 gram of second gas is 1 mole, but you have m2 gram. So how many moles are there? M2 by capital M2. So we have to put the values only this. So what we are going to get? In place of mu1, we have to write m1 upon m1, capital M1, into T1 plus m2 by capital M2 into T2 divided by m1 by m1 plus m2 by m2. So we will go with C option. We will go with C option. Next, the kinetic theory of gases gives the formula. We have that derivation. For the pressure P exerted by a gas enclosed in a volume V, the term N into M. What was N into M? The mass of 1 mole of the gas, the mass of the gas present in the volume V. So we know it was the complete mass which we take in that container. So it means the mass of whole gas present in that volume, we take that cuboid. So we are going with option B. Next, 27th. Which one of the following is not an assumption of kinetic theory of gases? The volume occupied by the molecule of gas is negligible. Yes, we didn't consider the size of molecule. Actually, what is the volume of gas? We take the volume of container, volume of gas. But according to the definition, what volume one molecule will get to move from here and there? That is the volume of gas. And in our container, there were n molecules. They occupied some space. It means for all molecule, free volume to move was not V. It was V minus volume of molecules. But we considered that, we assumed that the mass of each, volume of each molecule is 0. So each molecule is getting whole container to move here and there. So it was our assumption A. The force of attraction between the molecule is negligible. Yes. When one molecule was going to strike with the wall, the molecule behind this were pulling it, so it cannot strike with same power, but we didn't consider that force. So it was also in our assumption the force of attraction between two molecules was 0. The collision between the molecules are elastic. Yes, we assume this, that every collision is elastic, so there is no loss of energy due to collision. All molecules have same speed. No, we take C1, C2, C3. So it was not our assumption. So we are going with D option. Next, the average kinetic energy of a gas molecule is, we have complete derivation. The kinetic energy was proportional to temperature. So we are going with option D, proportional to absolute temperature. 29th, according to kinetic theory of gases, Molecules of a gas behave like inelastic sphere. No, inelastic means loss of energy. Perfectly elastic rigid spheres. Yes, we assume that perfectly elastic rigid spheres. So we are going with B option. Next, the average kinetic energy of the molecules of a low density gas at 27 degrees Celsius is, Boltzmann constant is 1.38 into 10 to the power minus 23 joule per Kelvin. We want to calculate the average kinetic energy of the molecule at 27 degrees centigrade. We know that kinetic energy of molecule is given by 3 by 2 kT. It was kinetic energy of the molecule. We have the derivation. All physical quantities are given. And units are also SI units. So no need to take tension. K, Boltzmann constant 1.38 into 10 to the power minus 23 joule per Kelvin. T, 27 degrees centigrade. Yes, it is not in SI unit. So we have to add 273 in this to get temperature in Kelvin. 273 and 27 means 300 Kelvin. So it is 300. So now cancel, remove this decimal with these two zeros. Cancelling 138 with 2. 2 6 are 12, 2 9s are 18. 3 into 3 9 because table of 9 is easy. So 9 into 69 into 10 to the power minus 23. What we are getting? 9 9s are 81, 8. 9 6 are 54 and 8 62. When we are writing in 10 to the power, decimal should be after one place after this. So 2 zeros are free, 6.21 into 10 to the power minus 21 joule. So we are going with option D.